In this video, we're going to talk about graphing kinematics. We're going to start by doing a graph review and looking at some of the major things that we look at on these kinematic graphs. We'll talk about position versus time graphs first, then we'll move to velocity versus time graphs, acceleration versus time graphs, and then how to change from one of these to the next. In physics, one of the most important things that we do is graph. And when we graph, we typically look at scatter plots. So let's talk about some of the most important things that you'll need to use and have on all of your graphs. Let's start with the axis. On your axis, you'll need to make sure to identify the independent and the dependent variable. Your dependent variable will go on the vertical axis, and your independent variable will go on the horizontal axis. You'll also need to make sure that these axes have their correct units of the things that you're measuring. Make sure to put these units in parentheses. Next, let's talk about your title. Your title needs to always go at the top, of course, but whenever you're doing your title, don't try to come up with something fancy, just do the basics. And by basics, you need to be very explicit about what it is. And your title will always be your dependent versus your independent. Once you have your axes labeled with the correct units and your title created, the next thing you'll start doing is to try and scale your axes. Make sure that all of these scales are consistent. So if you're going in fives, then make sure you go 0, 5, 10, 15, on and on and on. One thing that you can also do, if your data doesn't start at 0, you don't have to start at 0 either. So maybe on the bottom, you do start at 0 right here. But if you're going up, maybe your first data point is at 100. You can go from 100 to 110 to 120 and on and on and on and make sure that they are consistent and equally spaced. Also, whenever you're graphing, one of the important things that you want to do is you want to make sure that your graph takes up most of the page. So, if I was really graphing, I would hope that it would look a little bit more like this and that my data should be pretty spread out across the graph. And by that, I mean whenever I put my points on there, I don't need all of my data points to be right here at the bottom because that's hard to see. Make sure that your points are going to be somewhere scattered along like this to create your graph. Also, one of the things that you'll start noticing is with these graphs, sometimes you'll find a line of best fit. So that line of best fit, here it looks like it's just going straight up. So you may get to draw that line like this. On your line of best fit, sometimes you'll be asked to find the slope. Remember, slope is rise over run, or the change in the y's of the change in the x. This symbol right here is called a delta. It's one of the first symbols that you'll start getting used to in physics. It means change. And remember, if you're changing something, it's always final minus initial. You'll also need to make sure that you pay attention to your vertical intercept. A lot of times it's called the y-intercept. It means the same thing, but sometimes it's not always your y that's on that axis. So we get in the habit of calling it our vertical intercept. Using the slope and the vertical intercept, you can then draw the equation of the line or find the equation of the line using y equals mx plus b. When you use this form, the y stands for the dependent variable, the x stands for the independent variable, your slope is your m, and your b is your vertical intercept. Now that we've had an overview of what to look for on the graphs, let's look at a position versus time graph. Based on the title, that tells me that the position is our dependent variable, so that would go on the vertical axis. And our time is our dependent variable, which would go on the horizontal axis. In physics, the majority of the time, our position is based on meters and our time is in seconds. Now let's talk about reading our position versus time graphs. These are also called distance versus time graphs or sometimes displacement versus time graphs because displacement is the change in position. So on this graph, let's take a look at some of the things we talked about previously. To start with, our vertical intercept is 20. The vertical intercept will tell me our initial position because that's where I started. Then I can look anywhere on the graph to see where I was at what time. So for example, if I go up to 5 seconds, I had moved to 50 meters. This is 50 meters away from wherever the 0 point was. So it could be 50 meters from wherever we had a starting line, but maybe you got a head start at 20 meters instead of at 0. Also, one of the things that I noticed is that once I got to 5 seconds, as the time continued, I did not change position, which means that I stood still. So let's talk about the slope that you see on the graph. Your starting point or your vertical intercept is always important. Your slope is going to always be important too. So in this case, your slope on a position versus time graph is actually going to tell you your velocity, and this is why. Slope equals rise over run. And because my rise is position, I'm changing my position, and my run is time, and the time is changing. So that leads to rise over run, position, change in position over change in time. Change in distance over change in time equals average speed. But if we look at the flat line, we know that the slope of a flat line is 0. Also, if I don't go up or down any, it's 0 over whatever time is at the bottom, which means that my slope will be 0, so my velocity is 0. You may also be asked to find the velocity between time 0 and time 5 seconds. So let's find the slope of this part of the graph by using the same thing, the change in the vertical axis over the change in the horizontal axis. Start by identifying your initial and your final position. So we've already got our initial position at 20 and our final position is at 50. Once we have that, we can then use the same information to plug into our equation. Our initial time is 0 and our final time is 5 seconds. Now we can easily find the speed by solving for the slope. And our slope or our speed will be 6 meters per second. And I know it's meters per second because meters were on top. That was my Y or my vertical unit, and then my horizontal unit was seconds. So it would be meters over seconds. One more thing to consider whenever you're thinking about position versus time graphs is the sign on your velocity. Velocity means that you have not only a speed but a direction too. And whenever you're looking at your position versus time graphs, your slope will tell you whether it's going to be a positive or a negative velocity. Just like on a regular graph, if a line is going up, then you have a positive velocity or a positive slope. If the line is flat, then it's 0. But if you have a line that's going down, it is considered a negative slope, which would mean a negative velocity on this position versus time graph. You may also have a graph that extends beyond what we normally do a graph, and it looks more like a coordinate plane, and that is okay too. Continue to treat your graph the same, using the same rules that we've already been doing. You may just simply need to consider having a negative starting point or a negative velocity to go along with it. Now let's talk about a velocity versus time graph. The only difference between it and a position versus time graph is that velocity will be on the vertical axis and you'll still have time as your independent variable on the x-axis. Velocity is in meters per second and time will be in seconds. The vertical intercept will tell us our initial velocity or starting velocity. It does not tell you your starting position. You will only be able to find your starting velocity here. The slope is going to tell us our acceleration because slope is the change in the vertical over the change in the horizontal. If your velocity changes, that must mean that there is some acceleration. Just like when we were talking about position versus time graphs, the positive slope, the slope going up, means that you'll have a positive acceleration, and a flat slope would mean that there is 0 acceleration. This means if there's 0 acceleration, the velocity is constant. In this case, where the line is flat, it's technically a positive velocity. It is still moving even though you have 0 slope. There's just no acceleration or no change in velocity. And then the negative slope would be the line going down. Whenever you have a negative acceleration, it does not necessarily mean that you're slowing down unless you're getting closer to zero. But in some cases, just if you have a negative acceleration, you could be speeding up if you are in the negative sector. On this graph, now we have a positive velocity and a negative velocity, so we have another quadrant on our graph. The line, the horizontal axis, is zero velocity. So on section A, we have a positive acceleration because the slope is positive, but our car or whatever vehicle this is may be slowing down, or it is slowing down because it started at some negative velocity and it is approaching zero. If it's getting closer to zero, it's slowing down. Then once it hits zero, it's probably going to turn around and go the other direction because now it's turning a positive velocity. This positive velocity is getting bigger, so there is an acceleration there. At C, we have a flat line, which means zero acceleration, but we are still moving because we're still somewhere in this positive velocity area. D, we're going to start slowing down. It doesn't necessarily mean I'm slowing down because the slope is negative, but because I'm getting closer to zero. In E, I still have a negative slope or a negative acceleration, and I'm speeding up because I'm getting farther away from zero. F is a constant negative velocity. G is a negative velocity that is a positive acceleration because it's going up. It does approach zero, and then at the end, I have a constant velocity, a constant zero acceleration, and this is the only place on the graph where I would not be moving. And I know I'm not moving because my velocity is zero. The last thing we need to talk about with velocity versus time graphs is what does the area tell us? So in this case, we have a straight line that goes straight across. We have a constant velocity. That means we're not changing. However, we have talked about that just because the velocity is still constant, it's positive, we must be moving. And if we're moving, we have a displacement. To find this, we're going to multiply the velocity times time, or our vertical times our horizontal. So we'll say 6 meters per second times 4 seconds would be 24 meters. Not every velocity versus time graph will be a straight across example. Sometimes you may have slopes in with it, and you use the same idea that we have. The area under the graph is what tells us our displacement. So let's take a look at this example where we have some slopes and some flat parts where we can still the displacement using our area equations. The first thing you need to do is to make sure that you can identify your shapes. So in triangle A, I know it's a triangle. In this section right here, B, there's a flat line. Then I have this weird one below the horizontal line, and what would make my life a little easier is if I could make this part a triangle and this part a rectangle. That'll make solving for my areas a little bit easier. So let's find the area of each one. And by area, it means to be where's the line and where's the axis. So we'll look at this shaded part right here to make sure we can find the area. So part A is a triangle. Area equals 1/2 base times height. So we'll do 1/2 times 5 times 4. And that gives us 10 as our area. Part B is on the axis, so there's no room between it or anything else, so it has moved a 0 in that space. On part C, we have another triangle. However, because it's below the axis, we need to make sure that we pay attention to the negatives. So yes, your negatives do count here. So we'll say 1/2 times -2 times 1 second. That gives us a -1 as our area. Make sure to only use how many seconds have elapsed, not what second you were on. So instead of using 5 and 6, I used the distance between 5 and 6. Same thing for part D. Whenever we're looking at this rectangle, we have 4 wide times -2 tall. Area of a rectangle is length times width. So -2 times 4 is -8. Then the last thing we have to do is add all of these together to find our total displacement. Displacement is often represented by a delta x equals all of our areas added together. So 10 plus -1 plus -8 equals a positive 1 meter. So that means that even though we've traveled a lot, we've only ended up 1 meter away from where we started. The last type of graph that we'll cover in this video is an acceleration versus time graph. On these, the only two important things that we need are our intercepts and area under the graph. So the intercept, again, will tell us our acceleration or our initial acceleration. You'll notice that the ones we cover in this course only have a flat line, so the slope won't matter on the acceleration versus time graphs and what we cover. The area under the graph will be our most important thing on an acceleration versus time graph. Acceleration is the change in velocity over time. Well, on these, they're all rectangles. Area is length times width. So here we would say acceleration times time. If we look at those two equations, they're the same version. So in this case, our area is going to tell us our change in velocity. Now let's talk about changing from one type of graph to another. Here I have a position versus time graph. My y-intercept tells me my starting position, which is 0 in this case. My slope, I'll have to solve, is rise over run, but the area on a position versus time graph is of no use to me. So if we look at the slope, rise over run, I go up 10 and over 1, up 10 and over 1. That means my slope is a positive 10 meters per second. Let's draw that on the velocity versus time graph. Well, my slope was constant, or it was a straight line, so that means that my velocity never changed. I'm always going to be at 10 meters per second. So I can draw a straight line there. On a velocity versus time graph, the y-intercept tells us our initial velocity, which is 10. The slope tells us our acceleration, and because the slope is flat, that means the slope is 0, so there's 0 acceleration, meaning the velocity doesn't change. But now let's find the area under the graph. That's going to tell us our position. So if I look at this area, it looks like a rectangle, so I'll do 10 meters per second times 5 seconds. So total, I'll multiply 5 times 10, and that's 50 meters that was traveled in these 5 seconds. And that matches the position versus time graph, saying that I ended with a position of 50 meters, and I started at 0, so my change in position would be 50. Last, the acceleration versus time graph. If I look at my y-intercept, that's going to tell me my acceleration, and from the previous graph, it showed that the acceleration was 0, so my y-intercept is 0. I'll have to draw my acceleration to stay 0 on that axis. The slope is 0 because it's not going up, it's not changing, and then the area under the graph would be 0 also because it's on the axis. And remember, the area tells us our change in velocity, and so since the velocity didn't change, there was no acceleration.